Welcome to the Deep Dive, where we take a stack of information and, well, extract the most important nuggets of knowledge. Today, we're zeroing in on something really central to how applications run in the cloud. We're talking about Kubernetes.
Specifically Kubernetes pods,
Yeah,
right at the heart of it.
exactly. Our mission today is to give you a shortcut to being really well informed about these pods, what they are, why they even exist, how they function, and why they're just absolutely fundamental if you're doing modern software deployment.
Couldn't put it better myself. They're the building blocks.
Right. We've been digging into excerpts from a source called Understanding Pods, Kubernetes Deployment Foundation. And the idea is by the end of this deep dive, you'll have a really clear picture of these tiny but mighty components.
Sounds good. They underpin so much.
Okay, let's unpack this. So, pods. For anyone who's maybe heard of Kubernetes, maybe even used it, but found it, well, a bit daunting, where do we even start defining what a pod actually is? Like, what's the quick version?
Okay, so at its absolute core, a pod is the smallest, most basic unit you can deploy in Kubernetes. Think of it almost like a single instance of your application running in the cluster. It's essentially a logical wrapper. It groups one or maybe more containers together, and this grouping allows Kubernetes to manage them as one single unified thing.
A wrapper. I like that analogy. It helps frame it. So it really is the sort of atomic unit Kubernetes deals with.
Precisely.
And these wrappers, they must have some pretty specific characteristics, right? What are the key features that define a pod?
Oh, absolutely. They're quite distinct. First, there's container grouping. A pod can hold one container, which is common, or multiple containers that are designed to work closely together. They share resources like storage and network, and they operate under one specification. It really simplifies managing related processes compared to, juggling individual containers.
Okay, so grouping is key. What else?
Then there's shared resources. This is, I think, really powerful. All containers inside a single pod share the same IP address and the same port space. This means they can talk to each other super easily using localhost.
Think about microservices where components need very tight, fast communication.
Ah, right. Like they're on the same tiny machine.
Exactly. And they also share storage volumes, which is important for data. Another key point is their ephemeral nature. Pods are designed to be temporary, disposable. Kubernetes can create them, destroy them, reschedule them whenever needed, sometimes without warning.
Ephemeral, so you can't rely on them sticking around in one place.
Not really. And this design choice kind of pushes you towards building stateless applications, which inherently makes your whole system more resilient and easier to scale.
Okay, that makes sense. And scalability.
Yes, scalability. Pods are typically managed by higher-level controllers like deployments. These controllers handle scaling, spinning up more identical pods if you need more capacity, or scaling down. They also ensure availability. It really sounds like a lot of careful thought went into why pods exist, not just managing containers individually. Why did the Kubernetes creators land on this specific abstraction? What was the big problem they were tackling?
Well, think about managing containers in a big distributed system.
Yeah.
It's incredibly complex. Imagine trying to manually coordinate, say, a dozen containers across multiple servers, making sure they start correctly, find each other, share data. It's a nightmare. Pods abstract away a lot of that complexity. By grouping related containers, Kubernetes guarantees they run on the same machine, the same node, and they share resources efficiently. It just makes deploying, scaling, and maintaining applications so much more consistent and, frankly, manageable.
Right, it tames the complexity.
Exactly. It's a crucial layer of abstraction.
Okay, that clarifies the why nicely.
Yeah.
Before we dive deeper into the how, maybe a quick refresher for our listener. For someone familiar with K8s but maybe needs a reminder, what are those basic terms we should keep front of mind when talking pods?
Sure, good idea. So obviously, Kubernetes operates within a cluster. That's your set of nodes. Nodes are the machines, physical or virtual, that actually run your pods. Containers, as you know, are those lightweight packages holding your application. The control plane is the brain, the management layer making decisions, and Kubectl is the command line tool most people use to talk to the cluster.
Got it. Cluster, nodes, containers, control plane, Kubectl.
Right. And understanding pods is key because, well, they're the foundation connecting all these pieces when it comes to running your workload.
Okay, so we know what a pod is and why it exists as this foundational concept. Now let's get into the really interesting part. How do they actually work? What's going on inside, and what's their life cycle like?
Right. So pods are designed to run typically a single instance of an application, encapsulating everything it needs. They abstract the underlying container management. Structurally, you mainly see two patterns. First, single container pods. These are super common. Just one pod running one container, like say an Index web server. Simple.
Okay, the basic case.
Then you have multi-container pods. These are where things get more interesting. They contain multiple containers that are tightly coupled, designed to work together, sharing those resources we talked about. A classic example is having your main application container alongside a sidecar container.
A sidecar. Yeah, that paints a picture. What would a sidecar do?
Oh, various things. It can handle logging, pull metrics for monitoring, act as a network proxy, manage configuration, tasks that support the main application but aren't the core logic itself.
So these containers within the pod, they really do share resources intimately, like a little self-contained unit.
Exactly. They fully share that single network namespace, same IP, communicate via localhost. Super efficient. They can also share storage volumes. This lets them share data, maybe persistent data or configuration files. And the blueprint for all this, how the pod is configured, is the pod specification. Usually you define this in a YAML file, sometimes JSON. It specifies the containers, what resources they need, like CPU, memory, and other policies.
Okay, so you define this spec, this blueprint. Then what happens? What's the actual journey of a pod from definition to, well, disappearance?
Right, the pod lifecycle. It has a few key stages. It starts with creation. A user, or more likely a controller, submits that pod definition, perhaps using QVec to apply.
Okay, definition submitted.
Then comes scheduling. The Kubernetes scheduler, which is part of the control plane, looks at the pod's requirements and the cluster state. It decides which node is the best fit based on resources, constraints, policies, and assigns the pod to that node.
So it finds a home for the pod.
Exactly. Then the pod is running, or rather, it enters the running phase. Once assigned, the kubelet on that specific node that's the agent running on each worker machine gets notified by the API server. The kubelet tells the container runtime, think container or Docker, to actually pull the container images and start the containers defined in the pod spec.
And once they're running?
Monitoring. The kubelet keeps a constant eye on the pod's health. It uses things called liveness and readiness probes, essentially health checks, to see if the application inside is not just running, but actually ready to do work.
Right, those probes are important. And finally,
termination. Pods, being ephemeral, eventually get terminated. This could be because a user deletes it manually, or a controller decides it's no longer needed, or maybe the node it's on fails. If a node fails, Kubernetes often automatically tries to reschedule the pod onto a healthy node, assuming it's managed by a controller like a deployment.
so why is getting this life cycle and internal structure so important for us, for, developers or ops folks using Kubernetes? What's the practical takeaway?
Well, because pods are the fundamental unit for everything that makes Kubernetes powerful. They provide abstraction, hiding the messy details of individual containers. They enable scalability because controllers can easily manage many identical replicas of a pod template. And, crucially, they give you resilience. Kubernetes can automatically restart a failed container within a pod or replace a failed pod entirely, keeping your application available.
It really is the core mechanism.
It absolutely is. Understanding pods is understanding how Kubernetes actually keeps your application running reliably.
Okay, we've looked inside the pod, seen its life cycle, but pods don't live in a vacuum, right? They exist within this larger Kubernetes cluster. How are they typically managed in, let's say, real-world production scenarios? And how do they talk to each other or the outside world?
That's a great point. What's fascinating and sometimes trips people up initially is that you almost never create pods directly in production.
Really? Not using QVec to create pod.
Well, you can, but you generally don't for long-running applications. Instead, they're managed by higher-level controllers. These are like the managers for your pods. The most common one is deployment. Its job is to ensure a certain number of identical pod replicas are running. It handles updates smoothly, rollbacks if something goes wrong. It's your go-to for stateless apps.
Okay, deployments for managing replicas. What else?
There's the replica set. Deployments actually use replica sets under the hood. A replica set's simpler job is just to maintain a stable set of replica pods. Then you have stateful set. This is super important for applications that aren't stateless, like databases. Stateful sets manage pods that need stable, unique network identifiers, stable persistent storage, and ordered deployment or scaling.
Ah, for the tricky stateful stuff.
Exactly. And then there are job and cron job controllers. A job makes sure one or more pods successfully run to completion, think batch processing. A cron job runs jobs on a repeating schedule, like a traditional cron task.
So these controllers use pod templates to know what kind of pod to create and manage.
Precisely. They use a pod template defined within their own specification. This ensures all the pods they manage are consistent, and it automates the whole creation and management process.
So these controllers are orchestrating the pods, but how do the pods themselves communicate? If they're ephemeral and managed by these controllers, how does, say, my web front-end pod talk to my back-end API pod?
Good question. Communication happens at a few different levels. First, intrapod communication. As we said, containers inside the same pod share the network namespace, so they just talk over local host. It's very simple and efficient. Your web container talking to its logging sidecar, for example.
Okay, easy enough within the pod. What about between pods?
That's interpod communication. Every pod gets its own unique IP address within the cluster. So technically, pods could talk directly using these IPs. But remember, pods are ephemeral. Their IPs can change when they get rescheduled. Relying on direct IP communication is brittle.
Ah, right. So how do you solve that?
With Kubernetes services, a service provides a stable virtual IP address and a DNS name that fronts a group of pods, usually selected based on labels. When pod A wants to talk to pod B, or rather the service provided by pods like B, it just uses the service's stable address or name. The service then load balances the request across the healthy pods behind it.
Okay, services provide that stable endpoint. Makes sense. And getting traffic into the cluster, external communication?
Yes, external communication. Services are also the way to expose your pods to the outside world. You can define a service of type load balancer, if your cloud provider supports it, or node port. These mechanisms, managed internally by a component called kubeproxy on each node, make your application accessible from outside the Kubernetes cluster.
So services handle both internal discovery and external access.
Broadly speaking, yes. They're key for networking.
And all of this interaction creation via controllers, scheduling, kubelet running them, services directing traffic, it feels like it all needs a central coordination point.
Absolutely.
Yeah.
And that central point is the Kubernetes API server. It's the hub of the entire control plane. Think about it. You define your deployment, which includes a pod template in YAML. You can be able to apply it. That request goes straight to the API server. The API server validates it and stores the desired state in, etc., the cluster's database. The scheduler watches the API server for new pods that need assigning to nodes. It makes a decision and updates the pod status via the API server. The kubelet on the assigned node watches the API server for pods it's supposed to run. It starts them and then constantly reports their actual status back to the API server.
So everything flows through it.
Everything. Controllers watch the API server to compare desired state with actual state and make changes, like creating or deleting pods, by sending requests back to the API server. It's the single source of truth and the main interaction point.
Okay, tying this all together then. We've seen the structure, the lifecycle, the management, the communication. Why are pods, considering all this, just so fundamentally crucial to Kubernetes, and maybe by extension to how modern cloud-native applications are built?
Because they are the cornerstone. They enable modularity, group-related containers logically. They enable scalability. Controllers replicate these modular units easily. They enable portability. Because a pod defines its dependencies and environment, it can, in theory, run consistently anywhere Kubernetes runs. They encapsulate the application components and their shared context network, storage. They are the smallest deployable unit, the basic building block that the entire Kubernetes system uses to manage complex distributed applications effectively. Without the pod abstraction, Kubernetes wouldn't be Kubernetes.
What a deep dive indeed. We've really unpacked what pods are, how they function internally and externally, and their absolutely pivotal role in the Kubernetes ecosystem. They seem simple on the surface, just a wrapper for containers, but they enable everything else. Scheduling, scaling, networking, self-healing, often managed by those higher-level controllers.
That's right. And connecting this to the bigger picture, really mastering pods, how they're defined, how controllers manage them, how they interact through services, that understanding is absolutely essential if you want to effectively leverage Kubernetes. It's the foundation. All the more advanced concepts, all the cool patterns you hear about, they all build on this fundamental understanding of the pod.
So, for you, our listener, maybe think about this. How does this concept of the tiny, ephemeral, yet carefully defined pod manage through layers of automation? How does that abstraction empower these massive, scalable, resilient systems running so much of the modern internet? What does that tell you about the power of finding the right abstractions when you're trying to manage almost unimaginable complexity? Something to chew on. Thanks for joining us on The Deep Dive.